Right, so we worked it out to the equations that describe the variation of the orbital elements in a perturbed orbit. You disturb the orbit with a force given by a radial component, an azimuthal component, and a vertical component, and the orbital elements are going to be modified according to these equations. These equations are known as Gaussian equations. This all looks very abstract, but let's apply that to a specific problem. Let's use that to solve the problem of orbital drag. This animation shows a satellite on orbit around the Earth. Earth's atmosphere becomes a significant source of drag at altitudes below 1,000 kilometers. So objects in low Earth orbit are going to experience orbital drag. How can we predict what is the orbital decay? Orbital drag appears in the equation of motion as a term that is proportional to the velocity, operating at a drag time, tau. So you have gravity on one side, and then here you have the orbital drag. So because of the velocity, so we write to the velocity as r dot r plus r phi dot theta hat. That means that for orbital drag, we have that if the perturbation is df equal to r radial, t azimuthal, and vertical, then r drag is equal to minus r dot over tau. T drag is equal to minus r f dot over tau, and n drag is equal to 0. If we apply this to the evolution equations, we already see that there is no change in inclination, there is no change in longitude of the ascending node, so we are left with possible changes in semi-major axis, angular momentum, eccentricity, and argument of the perihelion. So to proceed, let's use again the expressions for r dot and rf dot. We have the dA dt is equal to 2a to the power 3 halves over square root of mu over 1 minus z squared times minus na 1 minus z squared e sine f over tau times z squared sine f squared minus na 1 minus z squared 1 plus z cosine f squared over tau. Now if you expand this is the evolution of the semi-major axis with orbital drag. For angular momentum, the evolution is more straightforward, since now t is equal to rf dot over tau, so this becomes simply dl dt is equal to minus r squared f dot over tau, and r squared f dot is the angular momentum. So you can already integrate this, dl dt. So dl dt is equal to minus L over tau, and you can immediately integrate that to find that the L as a function of time is equal to L naught and multiplied by an exponential. So the angular momentum will decay exponentially. Very clean solution that the orbital angular momentum decays exponentially. Now as for eccentricity, again with the definitions of R and T, we find that this becomes. So I have these two equations, one for the semi-major axis and one for the eccentricity that we don't know yet. Let's see what happens for circular orbits. If you have a circular orbit, then dA dt is simply equal to minus 2a over tau, and the variation of the eccentricity is minus na over tau times cosine f plus cosine v. Well, and for the circular orbit, the true anomaly and the eccentric anomaly are identical, so this becomes simply minus twice na over tau times cosine of f. So it seems that in part of the orbit, the eccentricity increases, and in part of the orbit, the eccentricity decreases. If you average out over the whole orbit, then the eccentricity does not change. It turns out that this is also the solution for eccentric orbits. So these are the equations for the orbital drag. The semi-major axis decays, the angular momentum decays, and the other orbital elements remain constant. We can solve that and find that the semi-major axis decays exponentially with twice the rate that the angular momentum decays. Now notice that this is only an orbital average solution. If you cannot do an orbital average, then you cannot eliminate the evolution of the eccentricity. In fact, for very elliptical orbits, where drag occurs only at periastron, this is a significant source of circularization.